Greetings and welcome to the Chemistry 221 final exam review video. And at this point, I hope to share with you a couple of questions that will help you prepare for the final exam in Chemistry 221. Now, the final exam itself will be over all the chapters of Chemistry 221, which is chapters 1 through chapter 7 in section 7.2, so up to 7.2. In this video introduction, though, I'm just going to show you some examples of questions from chapter 6 and chapter 7.1 to 7.2. This will give you a chance to get familiar with the most recent material and be good to go. Now, in the actual lectures that I give, what would happen is I'll put up a question, I'll wait a little bit for people to try and answer it on their own, and then I'll talk about the answer and they can see how they did, stuff like that. In this video, what I'll do is I will present a question. I will then ask you to pause the video for just a little bit, and well, you can work on it, and then when you have an answer, you can unpause the video, and then we'll talk about the answer, and you can kind of check yourself and see how you did. So it's kind of cool. It's a great way to prepare for the final, and you'll be good to go. In this page, I want you definitely to check with me to see if anything has changed since the time I made this video. But what I think is going to happen is the lecture final, all right, is going to have 20 multiple choice questions and 4 short answer questions. And it'll be over all the chapters 1 through chapter 7.2. So when you come to the lecture final, there's a couple of things you should bring. That includes definitely a calculator. That'll be important. Something to write with, a pencil. You'll want to bring the completed lab final, which I'll talk about here in a little bit. And you also want to bring the completed net ionic reactions lab. So the lecture final will be closed book, closed note. Can't use any notes. You will have access to a periodic table, which I will provide you. Should be about 2 hours in length, and you'll be good to go. Now, the lab final will be a take-home lab final this term, and it will be due at the time of your lecture final. And what I usually do is I release it Monday morning, super early, and then you can complete it before the actual lecture final where you'll turn it in. The lab final will probably be 6 short answer questions that relate to the different labs that we've done this quarter. You'll turn that in at the time of your lecture final. Make sure you turn in as a printed copy to receive credit, and it should be good to go. So the lab final is open note. You can look at the last labs and stuff that you've done, hopefully to prepare it, and it shouldn't hopefully be a big deal. I hope to have your final grades available by Friday evening. You won't get your final exams back. I hold on to final exams each quarter. I use them to compare term to term to see how everything's doing. And as always, good luck with your studying. I know there's a lot of material, but it's nothing you can't handle. If you've worked hard this whole quarter, and I bet you have because you're watching this video, you're going to rock this. So just take care of business. Okay, without further ado, let's start the review and see if we can help out here with some questions relative to the final exam. Which answer best represents the percent composition of the compound CO2, carbon dioxide? Now, carbon dioxide has carbon and oxygen in it, and one of those sets of percentages best reflects the percent carbon and the percent oxygen in the compound. See if you can figure this one out on your own. Pause the video, and when you're ready, unpause it, and we'll talk about how to solve this problem. Okay, I'm assuming you've tried this problem and you want to see how you did, and that's fantastic. If you're asked to find a percent composition, percent by mass, percent by weight, etc., all right, they're all the same thing, but not percent by volume, but we don't do that in chemistry. So anyway, percent composition, percent by mass, percent by weight, they're all the same thing. What you want to do is first find the molar mass of your compound. So in this case, you want to find the molar mass of carbon dioxide. And carbon dioxide's molar mass has 1 carbon and 2 oxygens. Carbon on the periodic table is about 12 grams per mole, and oxygen is about 16 grams per mole, and there's 2 of them. So the molar mass would be 12 plus 16 times 2. It's roughly 44 grams per mole. And you can do a better job with your sig figs than I've just done off the top of my head, but that will be good enough for this discussion. Anyway, once you've found the molar mass, then that goes in the bottom of the calculation, and on the top you put the amount of the element in that you're looking at. So for example, for carbon, we had 1 carbon, or 12 grams, So we would, percent carbon, you would have 12 grams divided by 44. 12 grams is how much carbon there was in the 44 grams per mole calculation we did. And for percent oxygen, you would take 2 times 16 in the top part, or 32, and divide by 44. So in this problem, here's the actual numbers worked out. And by the way, the answer is C. All right. So first of all, to more sig figs than I did off the top of my head, molar mass 44.01 grams per mole. And from that CO2 number, there was 1 carbon, 12.0. So 12.0 divided by 44.01, that comes out to be 27.3%. 2 moles, 2 times 16 is 32. So you do the same kind of thing right there. Percent oxygen, 72.7%. And if you've done this correctly, the two percentages together should equal 100%. So 72.7 plus 27.3 looks pretty awfully close to 100%. Another thing you can do is, if you had percent carbon at 27.3, why not just subtract that from 100%? That's an alternative way to find percent oxygen as well. So all of those are legit ways of finding these things. But again, if you need to find percentages, molar mass on the bottom and the amount of that particular element in the top. So for percent carbon, it was 12 in the top divided by 44. For oxygen, it was essentially 32 divided by 44. There's a whole series of nitrogen oxide compounds, all right? There's N2O, there's NO2, there's NO, there's N2O4, and the list goes on and on and on. One of the compounds has a percent nitrogen of 46.67%. We can use this information to calculate the empirical formula of this nitrogen oxide compound. So in this, we only have nitrogen and oxygen, all right? It gives us the percent nitrogen, so you can find the percent oxygen. See if you can use that information to find out which of those is the empirical formula of this nitrogen-oxygen compound. So pause the video, work on it, and unpause it when you're ready. Okay, I'm going to assume that you've worked on this question and you've got an answer. You want to check it out, and that's fantastic. Before we start, first of all, percent oxygen will be 100% minus 46.67%. So that number, whatever it is, that's going to be the percent oxygen. And the other thing is that all of those formulas listed, those are formulas based on moles. They're not based on mass. So in a problem like this, you've got to turn percentages into grams because they're mass percentages, and then grams into moles. And you can compare the moles that way to see what's happening. So let's do the nitrogen as an example here. You would take 46.67 grams. I am a big believer that you should just assume you have 100%, and that means 100 grams. So 46.67% nitrogen would be 46.67 grams of nitrogen. And we're going to take that grams of nitrogen and divide by the molar mass of nitrogen, which is roughly 14.01 grams per mole. And that's going to give us the moles of nitrogen we have. Now we're going to do the same thing with the oxygen. So it's about 53-ish%. Oh, you can do a better job than I can, but 53-ish% oxygen would be about 53 grams. We'll take that number and divide by the 16 grams per mole molar mass of oxygen to find the moles. Now, if the moles of N and the moles of O are about the same, then that means it's 1-to-1, and answer B would be right. On the other hand, if the moles of oxygen are twice as big, like if N was 0.5 and O was 1, then we'd have something like answer C. So we can use those mole ratios to figure out what's happening. So let's look at the math and the answer. First of all, the answer is answer B. It's 1-to-NO, nitrogen monoxide. Here is the 46.67% turned into grams. So 46.67 grams. And you want to turn it into moles. So you divide by 14.01 grams per mole, and this is the moles of N. Now, percent oxygen, like we talked about, 100% minus percent nitrogen. And that did come out to be about 53%, 53.33. Let's turn that into grams. So in 100 grams, that would be 53.33 grams of oxygen. Turn it into moles by dividing by 16 grams per mole. And this number is the moles of oxygen. Now, these two numbers, the moles of N and the moles of O, you can make a cheesy formula. N.3331 to O 3.333, but man, is that an ugly formula. All right, that's way too ugly for chemistry. So you need to break it down to whole numbers. You divide the bigger by the smaller. 3.331 is certainly is a little bit smaller than 3.333. So you can see that 3.331 divided by itself is exactly 1, and the other one is almost exactly 1. This is 1 nitrogen to 1 oxygen, or NO. Now, this is just the empirical formula. There is another step we'll talk about in a little bit where you can go from empirical to molecular formula, but this is the process, all right? If you have mass percentages, you first assume 100 grams, turn them all into moles, compare the moles to find the empirical formula. So this process works really, really well. We have 6.54 grams of zinc, and we're combining it with oxygen, and it makes some type of a zinc oxide, ZnXOY. And the zinc oxide, this white powder, has a mass of 8.14 grams. And we're going to assume here that all the zinc reacts. We can use this information to find the empirical formula. So what you should do on this problem is think about how to isolate the grams of zinc that reacted and the grams of oxygen that reacted. And if you turn those numbers into moles, you can compare the moles of O to the moles of zinc and see which of those seems reasonable. This is a good place to pause the video, and when you've worked through this problem, then unpause it and we'll talk about the answer. Okay, at this point, I'm assuming you've tried the problem and you've got an answer, so let's check it out, see how you did. In this problem, you want to find the moles of zinc and the moles of oxygen, and then you can compare them to each other to see which of those answers is right. Now, the zinc is easy. 6.54 grams of zinc reacted, and all of it was used up. So the first thing you want to do is turn 6.54 grams of zinc into moles of zinc. Now, the oxygen in this thing, 8.14 represents all the zinc plus all of the oxygen. So if you take 8.14 grams and subtract 6.54 grams from it, it's like all the zinc and oxygen minus the grams of zinc. That's going to give you the grams of just the oxygen. And that's how you found the oxygen, 8.14 minus 6.54. And from there, grams of O to moles of O, compare the moles of O to moles of zinc to see which of those is the right answer. In this problem, when you do this, you should get answer A. But let's look at how we get this. So first you got to find the grams of O. 8.14, which is the zinc and the oxygen, minus the zinc, that number gives you the grams of O, 1.60. And from the grams of O, you can find moles of O. Here's the molar mass. You can do the same thing for the zinc, 6.54 grams divided by the molar mass of zinc. You also get moles of zinc, and notice, of course, they're the same number. And that's exactly the same number, so there's really silly to compare, but I want you to see that just in case you have to if the numbers aren't the same. 1 zinc to 1 oxygen, the answer is zinc oxide, ZNO. Now, if you thought about the charges on the periodic table, you maybe didn't need to do this problem at all, or you could at least make a strong argument for what the answer should be. Zinc is one of the stairs. It's a positive 2 metal. And oxygen, when it's an oxide, oxygen's in group 6, 6 minus 8, oxide is also negative 2. So when a positive 2 zinc and a negative 2 oxygen come together, they will be 1-to-1 ZNO. Now that's not definitive proof, but that would be a strong argument for why answer A is correct. And as you can see, answer A was correct. Woohoo! So anyway, life is good. But it's another way to think about if this kind of makes sense. Here's a question. We have a compound with phosphorus and fluorine, and it's 75.41% fluorine. Stop right there. Percent phosphorus will just be 100 minus 75.41. This happens a lot of times. Chemists are too cheap to buy all of them. I don't know. But anyway, no problem. Anyway, after that, it says there's a molar mass of 251.94 grams per mole. 251.94, that's the molar mass of the whole compound. We can use this information to calculate the molecular formula of the compound. And there are 5 possibilities here. Now, this problem is basically a summary of the last couple problems we've done. You first want to find the percentages of P and F, and then turn them into grams, assume 100 grams, turn them into moles of P and F, and then compare them, all right? And you should get an empirical formula, some kind of PXFY, if you will, doesn't matter. Whatever thing you get, find the molar mass of the empirical formula and compare it to the molar mass of the whole thing, 251.94. That will be a whole number ratio, and that will be the number you multiply your empirical formula by to get the molecular formula. So all things we've done already, this is just everything all in one. Work on this problem a little bit. Pause the video, and when you're ready, unpause it, and we'll see how you did. I'm assuming that you've worked on this problem. You got an answer. Let's see how you did. So again, the idea here is first you want to find the percentages of P and F. You've got F, so 100% minus 75.41. That would be the percentage of phosphorus. And then those two numbers you want to turn into grams. I would assume 100 grams, so that means 75.41 grams of fluorine, because that's the percentage. Grams into moles. Compare the moles to find the empirical formula of the PF compound. And after you find the empirical formula, then find the molar mass of that. So add up the P's and add up the F's. If it equals 251.94, then your empirical formula and molecular formula are the same. On the other hand, if it's not, it's going to be a whole number ratio, and that whole number is what you need to multiply the empirical formula by to get the molecular formula. So there's a lot of math on this one. Let's start with the answer first of all. There's that part. The answer on this one is just going to be E. It's P2F10. So let's look at the steps here. I assumed 100 grams total, and 75.41% fluorine became 75.41 grams of fluorine. I turned it into moles, molar mass of fluorine about 19, 3.969 moles of F. Now, percent phosphorus wasn't given explicitly, but it's easy to find. 100% minus percent F equals percent P. There's only 2 elements here, 24.59%. And in 100 grams, that would be 24.59 grams of phosphorus. Turning it into moles, using the molar mass there of P, 0.794 moles. So we have a formula, but it's really ugly. 0.7940 moles of phosphorus for every 3.969 moles of fluorine. Pretty ugly. Divide both numbers by the smaller number. 0.7940 is certainly smaller than 3.969. So 0.7940 divided by itself is 1. That means 1 phosphorus. And 3.969 divided by 0.7940 comes out to be 4.999. That's pretty gosh darn close to 5. So the empirical formula of this compound, PF5, all right? Now that we know the empirical formula, our answer will be PF5 or P2F10 or P3F15, some integral of PF5. And to figure that out, we first need to find the molar mass of the PF5. So if you add up 1 phosphorus, 30.97, and add 5 fluorines, 5 times 19, you get this 125.97 number. That's the molar mass of the empirical formula. The molar mass of the whole compound, 251.94, divided by the empirical formula's molar mass, comes out to be a ratio of 2. And again, this ratio is going to be a whole number. So in this case, we'll take our empirical formula, PF5, and we're going to multiply it by 2. So that's where the P2F10 molecular formula comes from. If you have this down, you are good to go with the first midterm, all right? This is kind of the holy grail for chemists. So being able to knock these problems out is really important. If you did get stuck in anything, just make sure you know what to do, and you can go back later, look at other examples, practice and stuff will make this perfect. It's not a hard process to do. You just need to kind of work with it a little bit. And of course, if you have questions on anything, please let me know. I'm more than happy to help. Glyceraldehyde has an empirical formula of CH2O, and it has a molar mass of 90.08 grams per mole. And the question is, what is the molecular formula of this compound? And you've got 5 possible answers. So what I'm asking you to do here is how to go from an empirical formula and a molar mass to the molecular formula. This is a good time to pause the video and work on this problem. And when you're ready, when you have an answer, you can unpause it and we'll talk about what the answer is. Okay, I'm assuming you have an answer now to this problem and you want to hear it, so let's see how you did. An empirical formula is the smallest whole number ratio of atoms, all right? And the molecular formula, which is kind of like the holy grail of chemistry in this section, is the actual number of atoms in the molecule of the compound. So the answer here is going to be CH2O multiplied by some factor. So if you look at the answers, then A would be CH2O multiplied by 1, and that's legit. On the other hand, B is CH2O multiplied by 2. That would be C2H4O2, so that would be fine. Answer C is CH2O, the empirical formula, multiplied by 3. Answer D is CH2O, the empirical formula, multiplied by 4. But there's no way that this answer will be E, because E is not CH2O multiplied by some whole number. The hydrogens are wrong, all right? The carbon and the oxygen's fine, but hydrogen's not fine. That pulls the whole answer out. And what you need to do on a problem like this is you need to find the molar mass of the empirical formula. And the molar mass of the empirical formula might be the same as the molar mass of the whole compound, and it might not be, but that's what you need to do. Now, carbon about 12 grams per mole, hydrogen about 1 gram per mole, and oxygen about 16 grams per mole. So 12 grams per mole from carbon plus about 2 grams per mole from the 2 hydrogens plus 16 grams per mole for the oxygen. 12 plus 2 plus 16, that comes out to be 30 grams per mole. And 30 grams per mole, and again, you can do a better job on with your calculator and stuff than I can off the top of my head, but it's about 30 grams per mole, and that number is certainly not 90.08 grams per mole. So to find out how many empirical formula units go in your molecular formula, you would take the molar mass of the whole thing, 90.08, and divide by the molar mass of the empirical formula, which, as I said, is about 30 grams per mole. And you can probably see that's going to be a ratio of about 3. So let's go back and look at it. This number, 30 grams per mole, which is what I used here too, 30 grams per mole is the molar mass of the empirical formula of CH2O. There's the C, there's the 2 hydrogens, and there's the oxygen. The molar mass of the whole thing, 90.08, divided by the molar mass of the empirical formula will always give you a whole number. And that's why it's okay to be a little cheesy here. So this ratio, pretty gosh darn close to 3. So you're going to take your empirical formula and multiply it by 3. So the answer here would be C, C3H6O3. That is going to be the molecular formula. And again, you can go from the molecular formula back to the empirical formula, C3H6O3. If you divide each of those numbers by 3, that's where the CH2O thing pops in. That's why that is a reasonable answer. Molecular formula has to be empirical formula times some number. Now, sometimes empirical and molecular formulas are the same, and that's legit as well. If we would have found that the empirical formula's molar mass was equal to 90 grams per mole, then we would have said, okay, empirical and molecular formula are the same. But in this case, it was a 3-to-1 ratio. That's why we multiplied the empirical formula by 3. Let's say that we dissolve 6.73 grams of sodium carbonate in enough water to make 250 milliliters of solution, and the molar mass of sodium carbonate 106 grams per mole. What is the concentration of the sodium carbonate? Now, concentration in chemistry usually means molarity, moles per liter, so I'm just letting you know that. See if you can figure out the concentration of the sodium carbonate in this example. This would be a good place to pause the video. You can work on it, and then when you're ready, unpause it, and we'll talk about the answer. So pause your video now. Okay, I'm going to assume that you tried the problem and you want to see how you did, which is fantastic. So concentration is equal to molarity almost always in chemistry. We will see some other concentration units in Chem 222, but most of the time concentration and molarity go hand in hand. Molarity, the big M in those answers, stands for moles over liters. So in this problem, you want moles of sodium carbonate in the top, and you want liters in the bottom. Now, you've got to know how many milliliters are in a liter. How many milliliters are in a liter? If you said 1,000, you did a good job. Please know there's 1,000 milliliters per liter. We're going to use that a lot. So in this problem, you want to go 250 divided by 1,000. 0.250 liters is going to be the bottom, the volume term. The top part, the moles, you want to take 6.73 grams and divide it by 106 grams per mole. That'll turn your grams in per mole. So moles on the top, volume in liters in the bottom. This comes out to be 0.254 molar. That's the concentration of this solution. And you can see what I did down here, 6.73 grams divided by the molar mass. There we go. Divided by then again the volume in liters, 0.250 liters, and you have the concentration of the sodium carbonate, 0.254 moles per liter. 60 milliliters of 0.25 molar HCl are added to a 500 milliliter volumetric flask, and water is added to the mark. And it says, what's the concentration of HCl in the diluted solution? So this is an example where we're taking a concentrated solution, 0.25 moles per liter, and we're essentially adding a lot of water to it. So it's going to be diluted, which means the final answer will be smaller than 0.25 moles per liter. I would use on this problem M1V1 equals M2V2. So see if you can use that little hint and your knowledge of this section to figure it out. This would be a good place to pause the video, and when you're ready to hear the answer, you can unpause it. We'll talk about it. Pause your video now. Okay, I'm assuming you tried the problem and you want to talk about it, so let's get into it. So again, this is a problem where you have a concentrated HCl, you're adding a lot of water to it, so the final concentration will be less than you started with. So the answer will be a number less than 0.25. The moles of HCl here have not changed, and that's important. So for a problem like this, what I would do, M1V1 equals M2V2. You can also use MIVI equals MFVF or C1V1 equals C2V2. They all mean the same thing. But the idea is you have an initial molarity and initial volume, and then you're basically adding enough water to make this the new volume, what's the new concentration? So in the M1V1 equals M2V2, you essentially want to solve for M2. M2 equals M1V1 divided by V2. So what I would do on this problem is I would go 0.25 times 60, that's M1 times V1, and I would divide by 500. You do not have to change to liters here unless you want to. There's nothing wrong with it, but lazy chemists like me will prefer to just keep it in milliliters. And because it's V1 over V2, a ratio, as long as they're the same kind of volume units, you're good to go here. So in this problem, here you go, you can see M1V1 equals M2V2. I solved for M2. It came out to be answer C, 0.030 moles per liter. And again, I did not change milliliters to liters. If you're using this process, you don't have to. There's nothing wrong with doing it, but I would, again, kind of keep it there. If you ended up somehow with an answer which was larger than 0.25, then something was wrong in the calculation. These diluted things should be less than what you started with. So on this question, I would like you to find the sum of the alpha, beta, delta, and gamma expressions right there. And this might seem a little bit strange, but here's what I really want you to do. I want you to balance the reaction and then add up the little alpha, beta, gamma, and delta symbols that are in front of those four chemicals. And adding them up will give one of the answers on the left. So on this question, at the very least, balance the reaction and then see if you can add up those coefficients to find the overall value. So try to do this. At this point, pause the video and you can work on it. And when you're ready, you can unpause the video and I'll talk about the answer. Pause the video now. Okay, at this point, I'm going to assume that you've had enough time to work on the video and you figured out the answer. So like I said, what you want to do is you want to balance this reaction. So right now, you can see there's CH4, which is methane, oxygen, and that makes carbon dioxide and water. This is a combustion reaction. Something organic, which in this case happens to be methane, CH4, is being burned in O2 to make CO2 and water. And what I would usually do is I would try to balance the carbon and hydrogens first and do the oxygens last. So right now on the left-hand side, there's one carbon in CH4, and I would start then with one carbon in CO2. So initially I would have one for the alpha, and I would have one for the little delta right there. Now, for hydrogen, you can see CH4 has 4 hydrogens, and water comes in pairs of 2. So for delta right here, I would put a 2, because 2 times H2 would be 4 hydrogens, and that's the hydrogens we have there on the left. So that being said, now that I've balanced at least tentatively the carbon and the hydrogen, add up the oxygens. So CO2 has 2 oxygens, and remember we're having one right there for delta for the moment. So one CO2 would be 2 oxygens, 2 waters would be 2 more oxygens. So that means there's a total of 4 oxygens on the product right side. And on the left side, oxygen comes in 2s. It's one of the diatomics, have no fear of ice clear brew. So you write it as O2. Initially, I'm going to put a 2 right there. So I think that 1 CH4 and 2 oxygens makes 1 CO2 and 2 waters. And that sounds good. But what if you're not feeling confident about your results? And that's totally legit. So one thing that helps me is that sometimes I will make like a little spreadsheet, a little balance sheet, I guess would be a better name. And I'll have CH and O. And I want the CH and O on the reactant left side to balance the CH and O on the product side. And remember, tentatively, I have 1 CH4 and 2 O2s, making 1 CO2 and 2 waters. So on the left-hand side, 1 CH4 would give you 1 carbon and 4 hydrogens, and 2 O2s, 2 times 2 would be 4 oxygens. So if the product side has those same numbers, we'll be good to go. So 1 CO2 would be 1 carbon, and 1 CO2 has 2 oxygens. And then for water, we have a 2 in front of it. So that would be 2 times 2, 4 hydrogens, and 2 times 1, 2 more oxygens. And lo and behold, you can see there that we have 1 carbon on each side, 4 hydrogens on each side, and 4 equals 2 plus 2, so 4 oxygens on each side. So to add those up then, I would add up the 1 and the 2 and the 1 and the 2. So 1 plus 2 plus 1 plus 2, I'm going to think it's 6, answer B. Sure enough, answer B is the right answer. So if you see a question like this, don't be intimidated. Just balance the reaction and then add up the coefficients. Now, we wouldn't normally write a 1 in front of the CH4 and the CO2. We would just leave it blank. Having just the chemical there implies 1. We only put stoichiometric coefficients, those numbers, if there's more than 1. So you can see how the balanced reaction there, there's no 1 in front of the CH4 and there's no 1 in front of the CO2, it's implied. A 0 would mean the chemical wouldn't be there, and more than 1 is when you need them. But anyway, add them up, you got 6. Welcome to the world of combustion reactions, and this is totally stuff that you can do. What's the balanced equation for the combustion of butane, C4H10? So this is another example of balancing equations. One of those there is correct. See if you can work on it, and we'll go from there. So this would be a good place to pause the recording, work on the problem, and then when you're ready, unpause it. So pause your recording now. Okay, at this point, I'm going to assume that you have done this problem, and we'll check it out. A combustion reaction always has something organic, which in this case is this butane. Organic means carbon and hydrogen usually, sometimes carbon, hydrogen, and oxygen, something like that. And it will react with oxygen, O2, to make CO2 and water. So A is not correct, but it does show the raw ingredients. Something organic, C4H10 plus O2, CO2 and water are your only products. So at this point, what you want to do is you want to start balancing out different things. And like on the last example, I would balance the oxygen last, okay? And that's pretty important. Initially, C4H10, C4, I would put 4 CO2s because 4 C's on the left would balance 4 C's on the right. Water comes in pairs of 2s, so because there are 10 hydrogens in C4H10, I would initially put a 5 in front of the water. And having the 4 and the 5 there would balance the carbon and the hydrogen. But oxygen comes in 2s. It's one of the diatomics. Have no fear of ice clear brew. So on the product side right now, I would have 4 times 2, 8 oxygens from CO2 plus 5 oxygens from the water. That's 13 O's. And for O2, because it comes in pairs, I can't really have an odd number. What I'd like to do is have 13 halves O2, because 13 halves times the 2 of O2 would give me 13 oxygen atoms, which is what I want. However, you don't do that in chemistry. Chemists really hate fractions generally if you can avoid them. So instead of 13 halves, what we can do is multiply this whole thing through by 2. And if you do that, you get 2 C4H10s, and 13 halves times 2 would be 13 O2s. Multiply the other side by 2 as well, so 4 times 2, 8, 5 times 2, 10. Pretty sure answer B is right. Sure enough, it is. So that's what you'd want to do for this kind of thing. Try not to use fractions in your balanced chemical equations. It's bad form usually. And a combustion reaction is something organic plus O2 making CO2 and water, etc., etc. Good to go. Which of the following is the only insoluble salt in water? So this is a question now about solubility, and it makes you think about the solubility table we started talking about in the Chapter 4, Part 2 lecture. See if you can figure out which of these is the only insoluble salt in water, and when you're ready, you can unpause the video. So pause your video now. Okay, I'm assuming you've worked on it, you're ready to talk about it, so let's do it. Knowing the solubility table is something that will help us a lot in the next several sections, and also into Chem 222 and Chem 223. If you aren't a person that likes memorizing tables, and I totally understand, there are some kind of quick ways to get around these. There are some ions, if you look at that table, which are always soluble, always AQ. One of them is nitrate. Another one is sodium, like all the alkali metals. Potassium is another one. Lithium is another one. So you can see right away, I've underlined 4 of them. Wonder which one the answer is. But anyway, let me keep babbling here a little bit. Now, chloride, bromide, and iodide are usually AQ. So most of the time it's okay to say they're AQ, but they're not soluble when they're with silver, mercury, or, you guessed it, lead. So for all of those reasons, the nitrate makes that one water soluble. The sodium makes that one water soluble. Potassium makes that one soluble. Lithium makes that one soluble. And if you know the chloride, bromide, iodide exceptions, you can definitely say that, yeah, that's going to be soluble. So this one definitely answers C. Is going to be the one that's not soluble. We're going to run into the chloride, bromide, iodide, usually soluble unless they're with silver, mercury, or lead exception quite a bit. So I keep kind of pushing that on you. These ones down here, always AQ. So you could have sodium blah, 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 and you don't know what the heck blah, blah, blah is. You've never heard of it. Well, don't worry about it. The sodium makes that water soluble. So you would write AQ next to all the water soluble ones. But when it comes to PbI2 in water, you would put an S next to it. It is insoluble. It forms a solid. In this question, we have a reaction there, and it's balanced, but I'd like you to tell me what the spectator ions are, or what the spectator ion is in this reaction. So see if you can figure it out, and there's the possible answers right there, A through E. So what I would do is break this reaction down into the total ionic reaction, see which species are on both sides, those will be the spectators, and then we'll have a net ionic reaction when all is said and done. Okay, so see if you can figure out what all of this is. We'll talk about it here in a little bit. Pause the video now. Okay, at this point, I hope you've had enough time to work on the problem. Let's talk about the answer. To figure this out, you want to break down everything that is AQ into the cations and anions. But we're not going to break up the liquid water. We also wouldn't break up solids or gases if we had any. So what that means then is that KOH we would break down into K plus and OH minus. Anything that's AQ will break up into the individual ions. They don't stay together as the compounds. And for HF, we would break it down into H plus and F minus. Those would be the pieces that would happen. Now on the product side, we're going to do the same thing. We're going to break that down into K plus and F minus, but we're not going to break up water because it's a liquid. You don't break up liquid, solids, and gases. So now pieces that are on both reactant and product side are spectators. So if you see here, K plus is on both sides. So K plus is a spectator, but OH minus and H plus go in to make water, and those are different, so we don't want to break those down. But sure enough, fluoride there, F minus is on both sides. So in this reaction, the net ionic reaction would be just hydroxide and H plus making water. But for what we need, we want to know what the spectator's ions are. Spectator ions are the parts that we crossed out. So in this problem, that's going to be answer C, K plus and F minus. So you can quickly tell then what a spectator ion is because it'll be on both sides of the reaction and you are good to go. There's some equations listed here, and it says which equation below best represents the balanced net ionic equation for the reaction of magnesium carbonate with nitric acid. And there's all those different possibilities, or more information is needed. See if you can do this problem. This is a good place to pause the video, try out the problem, see how you do, and when you're ready, you can unpause the video and we'll talk about the answer. So pause your video now. Okay, I'm going to assume that you've tried the video and you're ready to rock and roll on it. So let's talk about it. So you've got to know a couple of things here. You have to know what the equations are, and you have to know what kind of reaction is going to happen. And if you look at answer A, all right, magnesium carbonate is MgCO3 and nitric acid is HNO3. And you can see here what's happening. This is an example of a double displacement or exchange reaction where the magnesium and the H's are trading places with each other. Now, magnesium with magnesium carbonate is positive 2, and if it's going to start dancing with negative 1 nitrate, it's going to be MgNO3 parentheses 2, magnesium nitrate. And H plus, when it dances with CO3, initially it makes what looks like carbonic acid, H2CO3. But H2CO3 is an unstable acid. It breaks down often to CO2 and water. This is an example of a gas-forming reaction, okay? So the equation on A shows all the pieces. Now, let's look at the states of matter. Carbonates are usually insoluble. The big negative polyatomic ions like carbonate, phosphate, things like that, usually insoluble unless it's with sodium, potassium, lithium, ammonium, stuff like that. Magnesium is not one of those, so that's going to be insoluble. But nitrates are always AQ. So you can see the HNO3 is AQ, MgNO3 is AQ, no problem. H2CO3, when it breaks down, makes CO2 gas and H2O liquid. Carbon dioxide is a gas. That's why this is a gas-forming reaction. So answer A is a balanced equation, molecular equation, if you will, for this reaction. It looks really great. But we're not looking for the balanced molecular equation. We're looking for the net ionic equation. And net ionic equation is just a reaction that kicks out the spectator ions. Now, there's several ways to do spectator ion analysis, but when you do this for a while, if you see a chemical species in an aqueous chemical on both reactant and product side, it's going to be the spectator. And if you look at the two aqueous pieces, HNO3 and MgNO3, well, sure enough, NO3 minus nitrate is in both of them. Nitrate is in HNO3, nitrate is in MgNO3. So what that means for us here is nitrate is a spectator ion, and your balanced net ionic reaction, you don't want to have any nitrate. You don't want to break up solids, liquids, and gases, all right? So don't break up the MgCO3. Don't break up the CO2 or the water. Don't touch the solids, liquids, and gases. The spectators will only be in the aqueous pieces. But sure enough, if you do look at B, the NO3s have been removed from HNO3, so you have 2H+, and the NO3s have been removed from magnesium nitrate, Mg2+. So answer B is the net ionic reaction here. This part right here, the first equation in the answer, that's what the equation, quote unquote, looks like when you do the balanced double displacement exchange. But H2CO3 is an unstable acid, and it quickly breaks down into CO2 and water. So be aware that one's weird. It's going to break down. And from there, that's the balanced molecular equation, or answer A. You can pull out the spectator, which is nitrate, to get the overall one. When you're doing gas-forming reactions, remember to look for H2CO3, and once in a while, you'll see NH4OH. That also breaks down to NH3 and H2O. That's a pretty sloppy N, sorry. NH3 is a gas, and H2O is a liquid. Let me rewrite that. Gosh, it's weird writing with this kind of pen thing here. So sorry, NH3 and H2O. So look out for NH4OH, and in this example, H2CO3. Which equation below best represents the balanced net ionic equation, so no spectators, for the reaction of potassium hydroxide and iron 2 chloride to give iron 2 hydroxide and potassium chloride? So in this problem, I'm basically giving you the names of all the compounds, and I want you to balance it, pull out the spectators, and give me the balanced net ionic reaction. Okay, so this would be a good place to pause, work on the problem, and when you're ready, you can unpause it, see how the answer goes. Stop your recording now. Okay, at this point, I'm going to assume you've worked on it, you're ready to check it out and stuff, and that's fantastic. All right, so we got to translate a lot of names into formulas. Potassium hydroxide, KOH. Hydroxide's OH -1, potassium's +1, KOH. Cool. Iron 2 chloride. Chloride's always -1. Iron 2 means iron +2. So you're going to need two -1 Cl's to balance that Fe2 plus FeCl2. It gives iron 2 hydroxide, so iron +2 and OH- makes FeOH2, and potassium chloride, K plus Cl minus KCl. So those are the chemicals you need. Notice, of course, like you have two Cl's on the left and initially only one on the right, so you need to have a big 2 in front of the KCl, and also to balance the hydroxides out, then you need a 2 in front of the KOH. States of matter. All right, anything with K, Na, NO3, etc. will be aqueous. So KOH and KCl, definitely aqueous. Chloride, bromide, and iodide, usually AQ, unless they're with silver, mercury, lead, and irons, or potassium for that matter, not any of them. So that's AQ as well. But FeOH2. Now, hydroxide is another one of these big negative polyatomic ions, and usually those are insoluble unless they're with sodium, potassium, whatever. Iron is not one of those, so FeOH2 should be a solid. So answer A is the balanced molecular equation for this reaction, and that's totally cool. Now, to pull the spectators out, you want to look at the aqueous pieces, and anything that's in an aqueous piece on both the reactant and the product side is going to be a spectator. So KCl on the product side will be a good place to tackle this. So K is aqueous in an aqueous compound on the product side, and K is on an aqueous compound on the reactant side. So K plus is a spectator. Cl minus is in this aqueous compound on the product side, and it's also in Cl as FeCl2, another aqueous compound on the product side. So both K plus and Cl minus here are spectators. You don't want to pull out the iron or the hydroxide though, because they form the FeOH2, the precipitate, if you will, in this reaction. So in this reaction, if you pull out the spectators, answer C should be the right answer, which is 2 hydroxides and Fe2 plus making FeOH2 solid. And again, this is the balanced molecular equation, which shows all states of matter. Pulling out the spectators, and there's 2 of them here, chloride and potassium, gives you the overall net equation. Again, never break up solids, liquids, and gases, so don't break up the FeOH2. Good to go. Which of the following statements is correct regarding the reaction of zinc plus VO2 plus 1? And you've got 5 different possibilities here. And notice there's a lot of terms: oxidized, reducing agent, reduced oxidizing agent, etc., etc. And there's even a possibility that it isn't a redox reaction. So why don't you go ahead and give this problem a shot, and you can pause the video, and when you're ready, you can unpause the video and see how you did. So pause the video now. Okay, at this point, I'm assuming that you've tried the problem and you want to see how you did, which is fantastic. This problem obviously is about redox chemistry or oxidation reduction chemistry. And you've got to know what reduced, oxidized, reducing agent, oxidizing agent means. My preferred way of doing this is through Leo the lion says GER. Leo stands for lose electrons oxidized. GER stands for gain electrons reduced. And there's several ways to do this problem. But what I would probably do is I would go through and find oxidation numbers of the different species. So let's do that real fast for this reaction. So zinc metal is zinc with all of its protons and electrons. It's elemental zinc. That's going to be zinc 0. All right, so that's not going to, just has an oxidation number of 0. Most of the time, the ions, the charge is their oxidation number. So that's a positive 1 right there. And the next one's a little bit tricky. Vanadium is all over the place, but oxygen almost always -2, like we talked about. So we have 2 -2 oxygens plus some unknown vanadium equals +1. So it's like, let me write that out. 2 -2 from the oxygen plus X for the vanadium equals +1. So if you solve for what this is, the X here is going to be the charge on the vanadium, and that comes out to be +5. Pretty sloppy. Sorry, +5. So the oxygen, -2, vanadium, +5. Wow, I cannot write +5 for some reason. Anyway, whatever. That vanadium is +5. Okay, keep going. Zinc on the right-hand side, product side, has a +2 charge, so that's going to be +2 zinc. The vanadium over here has changed now, but oxygen is still -2. So for the VO2 plus, we would say X for the vanadium plus -2 for the oxygen equals +2. So if you add 2 to both sides, you can see that this vanadium, +4. Oxygen, still -2. And then on water, hydrogen's almost always +1, oxygen's almost always -2. Now, using these oxidation numbers, you can see something interesting. Zinc has changed its oxidation number. It went from a 0 to a +2, all right? And the only way it can go from 0 to +2 is if it lost electrons. So the zinc here has been oxidized, all right? Zinc has lost electrons, goes from 0 to +2. It's also become more positive if that works for you. But zinc is the part here that's being oxidized. It is not reduced, so we can pull B and D out right away. Zinc is that. Also, because zinc has been oxidized, that shows that yes, this is a redox reaction. Something else apparently has been reduced and stuff in here, but because at one part's been oxidized, yeah, this is a redox reaction. Now, going back to the oxidation numbers, hydrogen is +1 on both sides. So hydrogen is not participating in the redox chemistry. And oxygen is -2 all the way throughout, which it usually is. So oxygen here isn't doing anything. But the vanadium, and let me write this up here because this is so sloppy. Vanadium went from a +5 in the VO2 +1 on the reactant side to a vanadium +4. That was the oxidation number of the VO2 plus. And so vanadium has also changed its oxidation number. Now, if zinc has been oxidized, you must have something being reduced. So we're going to hope that this vanadium is going to be a reduction, and we'll see. And if you figure it out, vanadium is becoming less positive, or vanadium +5 is gaining an electron to become vanadium +4. So vanadium +5 here is being reduced. Zinc has been oxidized and vanadium here has been reduced. So it might be tempting to go down and say, oh yeah, okay, well here's reducing. That's the same thing, right? And no. Reducing agent and oxidizing agent terms show up a lot in this kind of stuff. And again, I'm just the messenger. I didn't make these lame rules, but a reducing agent is something that has been oxidized. It's the opposite. If you see the agent, it's like the opposite. So reducing agent basically says that VO2 plus has been oxidized. And that's not the case, because we saw right here that vanadium is gaining electrons, it's being reduced. Something that's reduced is also known as an oxidizing agent. So I would say in this problem, Answer C is correct, and that is the correct answer here. So using oxidation numbers, we saw that zinc went to zinc 2 plus, that's been oxidized, or zinc is the reducing agent, that's okay too. We also saw that V and VO2 plus gained an electron to make VO2 plus on the product side. That shows that the vanadium is being reduced. We would call the VO2 plus one, we would call that the oxidizing agent. So knowing the terms is important. If you have one piece reduced, you have to have one piece oxidized. You can't have one or the other at this kind of level anyway. So be on the lookout for it, and definitely look out for those nasty agent terms. I don't like them, but again, I'm just the messenger, so alas. In this question, I'm asking you about the definition of what an acid is. And one of those 5 species listed is not an acid in aqueous solution. And I'd like you to try and figure out which one it is. So at this point, why don't you pause the video and think about it. When you're ready, you can unpause the video and we'll talk about the question. Pause the video now. Okay, at this point, I think you've had time to work on it. Let's talk about what exactly an acid is. So an acid is a species with hydrogen. And if you look at all of those formulas right there, all those species have hydrogen listed. Most of the time, if hydrogen is an acid, the hydrogen is listed first. So if you look at those species, B and D and E all have a hydrogen listed first. And the only time hydrogen is listed first, as far as I'm concerned, is if it's an acid. So B, D, and E are definitely acids. So we've narrowed it down now to A and C, which both have hydrogen. One of them is an acid and the other one is not. And at this point, you kind of just have to remember from lecture about what we talked about. A and C both represent the most common weak acids and weak bases. And for whatever reason, acetic acid is almost always listed CH3CO2H. CH3CO2 is the acetate ion when it has a -1 charge, and the H plus is the acid that goes on there. So what happens with acetic acid is that final H plus that's all by itself falls off, becomes H plus, and you have the acetate ion. I would prefer, as your teacher, that acetic acid was listed as HCH3CO2, but it doesn't usually work out that way for different reasons. I blame the organic chemist, but I'm an inorganic chemist, so that's probably not fair. Anyway, for whatever reason, acetic acid almost always CH3CO2H. It breaks the pattern of the acids. But the other species there, NH3, nitrogen-containing species, are often good bases. So C is definitely going to be the non-acid system. So most of the time, if you see a nitrogen, that will more likely be a base than an acid. And it's just the way. We'll talk about more about why this is in a future lecture. But anyway, ammonia is a weak base. It's a very common weak base, just like acetic acid is a common weak acid. The joys of chemistry. In this problem, one of those hydrogen iodine containing species is iodous acid. And I'd like you to tell me which one of those is iodous acid. So this is a nomenclature question for acids. See if you can figure out which one it is. Pause the video. You can work on it. And when you're ready, you can unpause the video and we'll talk about the answer. Pause the video now. Hopefully at this point you've had enough time to work on this problem and think about it, so let's talk about the answer. So hydrogen and iodine make a whole series of acids, and some of them are strong acids and some of them are weak acids. This is a question about being able to name the acid. In this problem, most of them have oxygen with them, and that's where it gets a little weird. If your acid doesn't have oxygen, it has a hydro prefix. So A, HI, with no oxygen, that would be hydroiodic acid, all right? So A is not the answer. Now, if you remember your polyatomic ions, IO3 minus is iodate. An iodate with the polyatomic with the AT ending is usually the most common polyatomic ion. An iodate, when it has an H plus next to it, makes an ic acid. So this would be iodic acid. All right, so HiO3 is not the answer either. Now, once you know the base, the common unit, if you add an oxygen to it, i.e. HiO4, answer E, it becomes peric acid. So that would be, in this case, since iodine is the central atom, E would be periodic acid. So answer E is not right. However, if you go from the base to one less oxygen, then the iodate becomes iodite, if you remember the polyatomic ions, and iodite with an H plus becomes an ose acid. Sorry, my pronunciation is really bad. I can't speak any language, I guess. But anyway, iodic acid is HiO3, and then one less oxygen becomes iodous acid. Now, if you happen to lose even one more oxygen, which does happen for iodine, chlorine, and bromine, you add a hypo prefix. So HiO is hypoiodous acid. But you can see here that definitely answer C is the right one. So what you want to do on these is, if you know the most common polyatomic ion, iodate, for example, for IO3, then you can build the other acids from there. So one more oxygen, peric acid. One less oxygen, us acid. And if you do have two less oxygens, then it's hypous acid. And again, always remember that no oxygen is the hydro prefix. Cool. Here's a question where there's several compounds listed, and it wants you to figure out how many of them are strong bases. So you can see there's NaOH, NH3, HNO3, KOH, water, LiOH, and acetone. And I'm asking you here to remember the strong bases that we talked about, because these will be very important in upcoming lectures. And also we'll talk about what the strong acids are. But anyway, see if you can figure out which of those answers is correct. Pause the video at this point, work on the problem. When you're ready, you can unpause it. I'll talk about the answer. Pause the video now. Okay, at this point, I hope you've had enough time to work on the problem. Let's talk about it, and then we'll see what the actual answer is. So strong bases, as well as strong acids, are going to be super important to us all the way through Chem 223. And in reality, there are more than 3 strong bases, which are the amount I want you to know. But these 3 are so important that they dwarf all the other strong bases, and you don't need to worry about it. Now, if you look at that list up there, most of the time, when you have an H listed first, that's an acid. So HNO3 is not a base at all. It's nitric acid. So that's flat out. Don't want to include that. Water is defined more or less as the midpoint between what an acid and a base is. So water doesn't really have acid or base properties. Don't have to worry about that. Acetone is actually an organic chemical. If you use a fingernail polish remover, you're actually using acetone to remove the fingernail polish. But anyway, the organic acids and bases aren't usually strong or weak, so acetone is not something you would want to consider for this problem. So what we have left here, NaOH, NH3, KOH, and LiOH. Now, in an earlier problem in this exam review, we talked about how ammonia is a very common weak base. But weak is the operative word. And what that means is that if you had, say, 10,000 ammonia molecules, maybe only one of them would actually become a base. So most of the time, NH3 just sits there. It's not a very good source of hydroxide, which is what you need for a base. So NH3 is a weak base, but it's not a strong base. However, if you remember from lecture, the 3 strong bases that I really want you to know, sodium hydroxide, potassium hydroxide, and lithium hydroxide, and they're all listed right there. So that answer here is going to be 3. There are 3 strong bases. Now, in addition, there's also 5 strong acids I want you to know. nitric acid, which we talked about earlier, hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI, and perchloric acid, HClO4. You need to know those 5 strong acids as well. So make sure you know the 5 strong acids and the 3 strong bases. You'll be good to go. Speaking of strong acids, in this question, I want you to figure out how many of the following are strong acids. And you can see there's some things from the previous problem and some that are brand new. So see if you can figure out how many of those are strong acids. So pause the video, think about it, and when you're ready, you can unpause the video and we'll talk about the answer. Pause the video now. Okay, I hope you had enough time to think about this problem. We will now start tackling this and see if we can figure out what the answer is. 3 strong bases we talked about last time: NaOH, sodium hydroxide, LiOH, lithium hydroxide, as well as KOH, potassium hydroxide. So this one is not a strong acid. It's a strong base, but it's not a strong acid. We also talked about in the last one how NH3 is the most common weak base. All right. So NH3, not only is it not an acid, it's a weak base. So that one's not going to fly. Water is usually the midpoint between when something is acidic or basic. So it's not going to be an acid. It's not going to be a base. It's just going to kind of sit there. Ethanol is drinking alcohol. And after going through videos like this, you probably want to experience drinking alcohol. No, just say no, kids. I promise, especially if you're under 21, 19 in Canada. But anyway, ethanol is something organic. It's not one of the strong acids. It's not really acidic at all. So ethanol is definitely flat out. So there are 5 strong acids that I really want you to know. HCl, hydrochloric acid, nitric acid, HNO3, hydrobromic acid, HBr, perchloric acid, HClO4, and HI, hydroiodic acid. And all 5 of them are listed there. All 5 of them are strong acids. So there are 5 strong acids in that list. Again, super important that you know the 5 strong acids and the 3 strong bases. You'll be good to go. Okay, that's the end of the exam review for the Chemistry 221 final exam. I'm really honored to have you here, and I hope this has been helpful. There's a variety of things to give you more practice: the practice problem sets, the concept guides, the chapter guides, end of the problems in the textbook. They're all there to help you out. And of course, I can help you out too if you have any questions. All right, good luck with your studying. Thanks for being here, and have a great day.